Okay, section 1.2 is titled Rate of Change. The objective is given a graph, table, or equation of a function. 1, estimate the rate of change at any given point. And 2, determine whether the function is increasing or decreasing. So there's lots of information for us to cover there. First thing is, if you look at the bottom of page 6 in your book, they just give you a quick review of the different types of functions that you have covered in previous courses. And I'm going to just quickly go through those here with you. You can take notes of these if you want to, but I would assume that these are things that you recall. The first three there, linear functions, quadratic functions, and polynomial functions. Remember, linear and quadratic functions are really polynomial functions of degree 1 and 2, respectively. And polynomial just kind of encompasses them all. Those are the most common that you're familiar with from previous courses. The next two are power and exponential functions. Those two, when you look at the graph, you got to be careful trying to distinguish between the two. Remember that the difference is where the x, the variable, shows up in a power function, it's in the base. It's x raised to some constant, versus in an exponential function, the x is in the exponent. It's some constant raised to the x power. That's the difference between the two in terms of their equation. The next, well, actually the last three here, rational algebraic. That means that you have a polynomial divided by a polynomial. Absolute value, as its name indicates there, is your standard function that involves some sort of an absolute value. And then finally, trig or circular functions that you studied extensively actually in pre-calculus, your sine, cosine, and so forth, all 6 trig or circular functions. And basically for everything that we're going to do in here in terms of radians versus degrees, basically everything in here will be done in radians. There's a reason why that is, and we'll talk about that later on. All right, so let's dive into rate of change. A rate of change, first thing we need to do is understand what a rate of change is. Now in the last section we understood that we covered instantaneous rate, and then instantaneous rate, another rate here, was another term that we use to describe a derivative. In fact, a rate of change is another word that we use to describe a derivative. And like I said, since we already know that's the same as an instantaneous rate, that's another word that we could use to describe a rate of change. In fact, sometimes we put those two words or those two phrases together and call it an instantaneous rate of change. Is another way to describe it. And the last thing that we'll definitely see this in a couple examples today, that another way that we describe a rate of change is a slope of a tangent line. And we'll see a couple examples of tangent lines sketched here, but if you were to sketch a curve and then draw a line that touches the curve in one spot, that one spot that's representing the slope doesn't cross the curve, it just touches the curve, that's a tangent line. We'll see that show up here in a minute. All right. Also in the objective there, you notice that it talked about 4 different representations of functions, or I talked about different representations of functions. There are 4 of them that we need to talk about here. And I'll go through each of these here with you. The first one is algebraic. An algebraic representation means that you're given an equation. That's probably the one that we're most comfortable with, that if I give you a function, the first thing you're probably going to ask is what's the equation of that function? An algebraic representation. F of x is equal to 2x plus 7 or something like that. The second form of a representation for a function is numerical, where you're given some sort of a set of data or table of data. If you think back to your science classes when you're doing experiments and collecting data, that data that you were collecting was actually representing a function, and it was a numerical representation of that function. The third representation is graphical, and as its name indicates there, probably the most obvious of these, it's just simply a graph. You're just given a sketch of a function, nothing else, just a sketch, and they might ask you to do something with that particular graph. In fact, our first example will start out like that. And the last one is verbal, which is some sort of a written description of a function. And they won't give you anything else, but based on that written description, you can still answer some questions. You might even be able to figure out what type of function that it would require to fit that description. And the last thing that I want to make a note of here in the objective, it talked about increasing and decreasing, so I just want to make sure we understand the difference between those and actually the relationship to a rate of change. And turns out that if you know something about the function either increasing or decreasing, you know something about its rate of change. In particular, the function increases if and only if the rate of change is positive. And vice versa if it's decreasing. If the function decreases if and only if the rate of change is negative. So if you know something about the function, whether it's increasing or decreasing, at the same time we know something about the sign of the rate of change, whether it's positive or negative. Okay? So let's take a look at our first example here. Example 1 there on page 7. And you can look in your book there, but it says it shows you a figure, as you see here on this slide down below. That says the figure there shows the graph of a function at x equals a, b, and c. State whether y is increasing, decreasing, or neither as x increases. And then state whether the rate of change is fast or slow. So the first thing I want to do is just kind of define for ourselves what we're going to conclude about fast and slow. And so for fast, we go to figure that out. When we look at the slope of the line that represents the tangent line, and we're going to look at that in just a second, if that's more than 45 degrees from horizontal, we're going to call that fast. It's increasing or decreasing very fast. And on the other hand, if the slope is less than 45 degrees from the horizontal, we'll say that that's slow. So that'll be our relative term that we all use. And if it's right on the border there of 45 degrees, then you're going to have to kind of decide which one of the two you're going to call. For the ones that we're going to see here, they're going to be pretty obvious, though. So that's how we'll define fast and slow. So let's take a look at what's happening at each one of these 3 points here. And I have a straight edge here, a ruler that I'm going to use to kind of help me illustrate this for you. But let's first indicate at this point A whether it's increasing or decreasing, and then secondly we'll deal with whether it's fast or slow. So x equals A. So at x equals A, as you look at the graph, again, increasing just simply means as we move from left to right, is the graph going up? Or decreasing means the graph would be going down. So as I move from left to right, I can see that this function is definitely increasing at A. It's on its way up. Draw in here just to kind of help us see that, but I can definitely see that as I go from left to right, that it's on its way up. So at x equals A, f of x is increasing. I'm just going to abbreviate that INC for increasing. You can do the same. And then to determine whether it's fast or slow, we just take our straight edge here and just slide it over to this function. And I'm going to put this straight edge kind of on that curve. Notice I come in from the concave side of this thing and just try to cover up everything except for that one point there that we're considering. And that is the edge of the straight edge that you see there is in fact the tangent line. In fact, I can even sketch that in here if I just draw this line in. We can move our ruler out of the way. That line there represents the tangent line to this curve at x equals A. And so we're using that as our judgment for fast or slow. Is that making an angle greater than or less than 45 degrees from the horizontal? And I think we can definitely see that's more than 45 degrees. In fact, if you look down there on my ruler at the bottom of it, it says 72 degrees. So definitely it's much deeper than 45 degrees. So it's increasing fast, we'll say. And now let's jump to x equals b. X equals b. We do the same analysis. X equals b is over here further to the right. And so the question is this thing increasing or decreasing? First of all, I can see that at x equals b, that this graph is definitely on its way down. So the graph is decreasing, so f of x is decreasing. And again, we're going to kind of use the straight edge to approximate what's happening here. I'm just going to draw kind of the line in that would show up if we were to put the tangent line in this graph. It would look something about like this, which looks pretty close to 45 degrees with the horizontal, actually. But I'm going to go ahead and say that this is slow, because it's definitely slow in comparison to the point A. So I'm going to say it's decreasing slow. And then finally, they asked us what's happening at x equals c. So at x equals c on our graph, we come back up here to the graph. If I were again to draw in the horizontal, or to draw in the tangent line, there would be a horizontal line it would look like. Something about like this. So in that case, it's neither increasing nor decreasing. It's a horizontal line there. It's not going to increase or decrease. So f of x is neither increasing or decreasing. And since it's not doing either, we don't have to indicate whether it's fast or slow there either. Okay? So there's not a lot we can get from just a graphical representation of this function, but there is some things that we can get out of it. Okay? Let's take a look at the next example here, example 2. Page 7 says, the figure there shows the graph of a function that could represent the height, h of t, in feet of a soccer ball above the ground at as a function of the time t in seconds since it was kicked into the air. Estimate the instantaneous rate of change of h of t at t equals 5 seconds is part A on this thing. So again, what we're going to do is use a straight edge to kind of help us mark this tangent line in here. So let me just grab my straight edge, and I'm going to, again, come in from the concave side of this thing as I do this. And I'm trying to cover up everything on this graph except for that one point. And then I'm going to sketch the tangent line here. It's the line that goes right down the edge of that ruler. Okay. And I don't need this ruler anymore, so I'm just going to move him out of the way. And my goal here then is to come up with an approximation for the slope of that tangent line that I just sketched there. Okay. They wanted the instantaneous rate of change. And that's one way to calculate it is to find the slope of this tangent line. So what I'm going to do is I'm going to just pick, since I know slope can be calculated as rise over run. Or another way to calculate slope of that line is I can actually pick 2 points that are on that line or that it goes through and find the difference in the y's, so it's y2 minus y1, over the difference in the x's, x2 minus x1. Either one of those will, of course, give me the slope of that line. So I already have one point that it goes through. It goes to this point right here, which is at x equals 5 and y equals 60. So this is the point. I'll go ahead and name that point up here. That's 560. And the next thing I'm going to do is I'm going to pick a run, and I'm just going to kind of illustrate it up here. I'd suggest that you pick more than one unit horizontally to run. In this case, I can actually make a run of several units, so I'm going to go ahead and do that. But I'm going to go from this point here. I'm going to go across, we'll say to here. So I'm going to go from 5 all the way, in this case, to 9. So that's a run of 4 is what we're looking at right here. And you can see the corresponding rise, or actually technically in this case it's a fall, right? We're actually decreasing here. And I need to calculate that that rise or that fall in this case. But really what I need to do is I need to come up with a name for this point right here that this tangent line goes through. So I already know it goes through this point up here at 560. If I can find this point here, that will give me 2 points. I can find the slope of this line. So I know the x value there because I chose to run is at 9. And the y value there, I'm going to have to approximate it. Your units here that are indicated over here on your y scale are incrementing in units of 10 there. So it looks like that might be a y value of, I'm going to say 2, maybe 3. In fact, I'll go ahead and say it's 3. So we'll say that's at 0.93. All right, again, it's an approximation here, so you might say it's 2, you might say it's 4. Those are probably close enough to what we're looking for here. So based on that, you can determine the rise or the fall in this case, really, since I know that it started up here at 60 and we went all the way down to 3. That means it's a fall of a negative 57. It actually is negative here because we dropped 57 units. That's why I say it's a fall. So you can decide how you want to calculate the instantaneous rate here, whether you want to do rise over run, or the change in the y's or the change in the x's. You can do either one to get the answer here, of course. So the slope is equal to, if you do rise over run, that's going to be a negative 57 divided by 4. Or if you look at this as being, the slope is equal to the difference in the y's over the difference in the x's, that'd be 3 minus 60 in the numerator over 9 minus 5 in the denominator. Notice that gives you a negative 57 over 4. This is why I say it doesn't matter which way you do it, you're going to get the same result. So in either case, if you punch that into your calculator, negative 57 divided by 4, I'll just quickly punch that in my calculator. And we get a negative 14.25. So that's a pretty good approximation for what the instantaneous rate of change is at that particular point in time. Now, the one thing we do need to indicate is units, and we realize that if you go back to the slope equation here, in particular, I like looking at the second one, because this is the change in y values over the change in x values. And if you look at what the units were on your graph, the y values were measured in feet, and the x values were measured in seconds. So I was actually taking the y values, which are measured in feet here, divided by the x values that were measured in seconds. So my calculation is then feet over seconds, or that would be feet per second. Make sure you indicate units where appropriate in your problem. In part B, give a mathematical name of this instantaneous rates, and so it's called a derivative, of course. And why is it negative? Well, it's negative, we've said that several times, because our function was decreasing here. That means that the rate of change has got to be negative. If the function were increasing, the rate of change would have been positive. All right, let's take a look at one more example. We're going to actually skip over example 3 and jump to example 4. Example 3 is very similar to problems that you did back in section 1, so I'm only skipping over it for the purpose or for the reason that you've already done problems like that. We certainly could look back at example 3. That's a very good example if you need a little more assistance with section 1. Example 4 says you have a mass that's bouncing up and down on a spring hanging from the ceiling. Its distance y in feet from the ceiling is measured by a calculated distance probe, each 1/10 of a second. Given this table of values, which I have up here on the slide for you, I also have a picture of the mass as well. Given this table of values in which t is in seconds, they want you to do the following. Part A in the question, we're not going to do all part A, I'm going to just do part 1 of A. It says, how fast is y changing at each time? So I'm going to find out at t equals 3 seconds. Realize that you would do the same process for the next two at 6.6 and 1.0 seconds. But I'm going to just focus on what's happening at t equals 0.3 seconds. So if you recall what we did in the last section to handle a problem like this, is we said, well, the way that we can find the instantaneous rate here, or to find how fast it's moving, is to find the rate, actually an average rate, on a small and then smaller and smaller and smaller interval. Well, unfortunately, we can't quite do that here. I'm limited by the set of data that I'm working with, so I can't really make this an interval that gets smaller and smaller and smaller. What I can do is I could actually find the rate of change, though, from 0.3 seconds to 0.4 seconds. So I could actually find the rate between 0.3 and 0.4. But we saw yesterday that in section 1 that was probably not the best size interval to use because it was give us definitely an answer that was not as accurate as we were hoping for. When we started making that interval smaller and smaller, we got much better answers. And so in this case, it would actually be just as well, but not only I looked at what's happening from 0.3 to 0.4, but I also looked at what was happening from 0.2 to 0.3. Took both of those times into account, what's happening just before 0.3 seconds and what's happening just after 0.3 seconds, and used the combination of those two to get my best approximation. Now it turns out you can actually calculate those two rates individually and then average them, or it turns out that's the same as just calculating the rate from 0.2 to 0.4 seconds. Okay? So I'm going to call this my average rate here, like we did before. My average rate is, I'm going to write this out actually a couple ways for you. You can decide which one you like best. My function that they call here is y, so I could say this is y evaluated at 0.4 minus y evaluated at 0.2. Divide that by the difference in time, 0.4 minus 0.2. The other way you could do this, because I actually have the y values sitting right here in front of me in this table, is I could actually just plug those right into my formula here. So I could say instead y at 0.4 is the 7.37, and the y at 0.2 is 3.99. This is how I would prefer to write it, and that's how I will write it actually in the second form. You do not need to write both of these, just one is sufficient. You pick which one you prefer. The first form looks a lot like what you did in section 1 using function notation. However, the second form, since you have the y values right there in your table, there's no reason not to write them down, I guess. So let's go ahead and punch that into our calculator and see what we get. And if you punch that in, you'll find that you end up with 16.9. And again, add units where appropriate. So this is taking the change in the y values. I like this function notation to help us find the units here. Change in your y values, and your y values up here were measured in feet. Over the change in your x values, and again, if you go to your table over here, your table, you'll see that those were measured in seconds. So our units then are a change in feet over change in seconds. That would be feet per second. 16.9 feet per second. All right, and again, you can do the same thing for t equals 0.6 and 1.0 seconds and get similar results. Some of them might be positive, some of them might be negative. It says that for part B, at t equals 0.3 seconds, is the mass going up or down? And justify your answer. Well, if you go back to the answer we came up with, it was looking at the rate. It was moving at 16.9 feet per second. So I know how fast it was moving. And the key here is that it's a positive 16.9. The fact that it's positive tells me that the y value must actually be increasing. Again, if the rate is positive, your function was increasing. If the rate was negative, your function must be decreasing. So if y is increasing, that means that this distance right here is getting bigger and bigger and bigger. And if that's the case, then my mass must be moving down. So the mass is moving down. Okay? Now again, for each of these problems, you have to go back and carefully analyze how they're measuring y. In this case, they're measuring y by measuring the distance from the ceiling to that mass. If, on the other hand, they had measured, say this is the floor, and they were measuring y this way, that y was now the distance from the floor to the mass. And now you can see that if y were actually getting bigger, in this case, that the mass would have to be moving up. So you got to always go back and consider how are they measuring this distance y in order to determine whether it's moving down. So that gets to do with our example with the door opening and closing. Okay? All right. That is the end of section 1, 2.